Okay, the first part of section 5 is doing this problem, matching up the graphs with the functions. So what you're supposed to do is you're supposed to look at the limits as x approaches infinity of the functions and see if those, if you can match those up with the graph. So let's look at problem 3 first. So what you have is 3 over x squared divided by x squared. So we just look at the higher order terms, and so this is the we'll call it the horizontal asymptote. So you're going to have 3 divided by 1. So it's 3, and it goes to the same limit when x is goes to infinity or negative infinity, because they're both squared. So let's look at the picture over here, and there's 2 functions that have a limit of 3. There's this one here, and there's this one down there. So if you look at the actual value of the function when x equals 0, you get 0 over 0. So if you think about that, it's kind of like, let's just think here, as far as, you know, it's an indeterminate type result. No, you don't get 0 over 0, you get 0 over 2. It's because you get 0 here, and you get, so the limit is 0. That value, sorry, the value of the function at x equals 0 is 0. So this one's 3, this one's 0. So as a consequence, the answer to problem 3 is curve F, because it has a limit of 3 as x goes to positive and negative infinity, and the value of the function is 0. Okay, let's go to 4. Let's skip over that because that has a square root, so that's the hardest one. Here we have x to the first power divided by x squared. Again, we only look at the highest order terms, and it really doesn't matter what the coefficients are in front. When this number is less than that number, then the horizontal asymptote is equal to 0. So how many do we have here that have 0 horizontal asymptotes? This one does, and this one does. Now, they both have also a value of the function of 0 at x equals 0. So it could be either b or d. So which one would it be? Well, let's just write b or d right now. Well, is there any way we can... Well, one way you could look at this function never gets greater than 1. So the question is, does this function ever get greater than 1? And the answer would be, again, the value of the function is 0, because you get 0 divided by 0 squared plus 2. So you get 0. And if you put x equals 1 in there, you get 1 divided by 1 squared, which is 1, plus 2, so you get 1/3. So that one's equal to 1/3 at x equals 1. This one's equal to over 1. So we can say that's D. And 7, well, let's go to 6. So again, looking at this term, what happens when x goes to positive and negative infinity? Well, this one's to the 2nd power. This is to the 4th power. So this thing goes to 0 at plus or minus infinity, because this is less than that. So it has a horizontal asymptote of 2. So we look at this, and we see this one has a horizontal asymptote of 2. This has a horizontal asymptote of 3. So by that, just that itself, we can say that this is E. And you can also check it if you look at the value of the function at x equals 0. This whole thing goes to 0. So the value of the function should be 2. So where's the function we were just talking about? This one here. Well, that's interesting. That card. Oh, this one actually has, this has plus or minus, so that doesn't work. So let's think here. This has a value of 2 at x equals 0. See, that one doesn't work for that. So, Well, let's come back to that one. I don't know why I'm not seeing it right now, but let's go to 8. Okay, so we have this to the second power, this is the second power. So you ignore the higher order terms and you look at the leading coefficients. So the answer is 2. The horizontal asymptote is 2, just like this one is 2. But the value of the function, so if you do f of 0, which is easy to evaluate, you get 5 over 1, which is this one here. So this has a value of 5, has a horizontal asymptote of 2. So that one is E. So that other one is not E because we already figured that one out. We just weren't sure which one it is. Okay, so that one's E. This is 4 times the sine of x over x squared plus 1. So what's the limit here? Well, this just goes between -1 and +1. This goes to infinity, so it's going to approach 0. So the horizontal asymptote of this one is 0. And there's 2 that have kind of a periodical nature to them. Well, really there's only one. It looks like it has it. If you put x equals 0 in, you get the sine of 0, which is 4 times 0 over 1, which is 0. So that looks like this is C. So what do we have left? We have A and B. So this one has to be either A or B. Oh, yeah, I don't know. This one has a horizontal asymptote of 2 and a value of the function of 2 at 0. So that one is easy. That one's A. So we have A. Oh, that's not right. This is not. How did I get C? That's not correct. I said that was B. So this must be C. And that's one characteristic you see of things where there's a square root of something squared. We'll see that later in later problems, is that you have the opposite. You get a positive number here, in this case +2, and this one is -2. So that's sort of characteristic of that particular type of function. So let's kind of review this now that we've gone through it. This has a horizontal asymptote of 3 and a value function of function 0. So this has a value of the function here 0, 0, and horizontal asymptote is +3. This one had that square root thing in there, so we can pick that one out where it's not the same on both sides of the origin. 5 was D because it had a horizontal asymptote of 0, and the value of the function at, say, x equals 1 was a third, and this one was a third, but this one was not a third, so that didn't work out, so it must be D. 6 was 2, the value of the function was 2, and the horizontal asymptote is 2 because this part goes to 0. So the only one that has that characteristic is A. 6 was a sine function. It has to have some kind of periodic nature to it. It has a horizontal asymptote of 0 because this is finite and this is infinitely large. So you get something finite divided by something infinite gives you 0. And then this one had a horizontal asymptote of 2, but the value of the function was 5 by setting x equal to 0. If I go back here and I erase that, you can see when x equals 0, these terms drop out and only have us 5 divided by 1. And so that was the one function that had the value of the function 5, and it also had a horizontal asymptote of 1. We're on problem number 18 now. These are finding the limits of each case. And they look similar, but they're different, so that you get different answers, of course. So 18, we have 3 expressions. We have the limit as x approaches infinity of 3 over 2x divided by 3x squared minus 3x cubed minus 1. And that's the same as negative 2x minus 3 over 3x cubed minus 1. The reason I did that is just to put the x term to the left-hand side. So we can look at the highest order terms, which are these two. This has an exponent of 1, this has an exponent of 3. Since 1 is less than 3, the answer is 0. Now the second thing is we take the limit as x goes to infinity of 3 minus 2x over 3x minus 1. So again, I'm going to put a negative, well, I'll just put it out front. Negative 2x plus 3 over 3x minus 1. That's the limit as x goes to infinity. And remember, what the difference is between what we did now, what we're doing now, and what we did in pre-calculus was we're just talking about horizontal asymptotes as a limit, defined in terms of a limit. Okay, so because these are both to the first power, you take the ratio of the leading coefficients. So the answer is negative 2/3. And then the third one, the limit as x approaches infinity of 3 minus 2x squared over 3x minus 1, which again, I can rewrite this. So you have negative 2x squared plus 3 over 3x minus 1. This has an exponent of 2. This has an exponent of 1. Therefore, the answer is it does not exist. Or you could say negative infinity if you wanted to give a number, because it's negative because this coefficient is negative. Is that true? Actually, it's positive. Well, actually, it depends upon, it's negative because these are both positive numbers. Positive infinity squared, positive infinity. So they're both positive, so it's just the sign of the coefficients, which is negative 2/3, so it's negative infinity. Problem number 22. So we have the limit as x approaches positive infinity of 3x cubed plus 2 divided by 9x cubed minus 2x squared plus 7. Okay, we look at the highest order terms. They're both raised to the third power. So the rule says that the limit is just the ratio of the leading coefficients, which we can then simplify to 1/3. So we're looking for the limit as x approaches infinity of 4 plus 3 over x. Then we can actually do those separately. If we break it up, we can take the limit as x approaches infinity of 4 plus the limit as x approaches infinity of 3 over x. Well, the limit of 4 as x approaches infinity is just 4. It's just a constant. And the limit of this is 0 because you get 3 over infinity, which is 0. And so the answer is 4. So we have the limit as x approaches negative infinity of 5x squared over x plus 3. So that's raised to the first power. 2 is greater than 1, so this is going to either approach negative infinity or positive infinity. So we really don't have to worry about that term at all. And so you'll have negative number squared. So that's going to be positive. And then the number in the bottom is going to be negative. And so the answer is negative infinity. So this has a positive sign, so we really need to write that. This is positive, and this is negative. So you end up with negative infinity as the limit. So what are we doing next? Number 20 to 25. Number 30. Okay, yeah, that's the one that's that special kind. The limit as x goes to negative infinity, negative 3x plus 1 divided by the square root of x squared plus x. So what do we do? Well, if the limit is going to positive infinity, we could use that x is equal to plus the square root of x squared. So if we're taking the limit as x goes to positive infinity, we could say x is equal to plus the square root of x squared. We're the other case, where x is going to negative infinity, so we can say is x is equal to negative the square root of x squared. That's because if you take the square root of a number, it can be either plus or minus. So if we take the negative square root times the negative gives us a positive. So what does that do for us? Let's do the math here, and then we'll do the limit once we get everything straightened out. So we're going to multiply by x and divide by x. So we're multiplying by essentially 1. In the numerator, and actually we're dividing by it, sorry. So we're going to multiply by 1 over x. So this is 1 over x. This is 1 over x. And let's put a parenthesis around that so we're clear about what we're multiplying by. In the numerator, I just leave it as 1 over x. In the denominator, I change it to negative 1 over the square root of x squared. So x is negative x squared, negative the square root of x squared when you go to negative infinity. So the numerator becomes negative 3x divided by x plus 1 times 1 over x, which is 1 over x. In the denominator, the minus sign, negative sign stays out. But what happens is this time 1 over the square root of x squared times that, basically the x squared comes in. So we divide each one of these terms by x squared. So x squared becomes x squared divided by x squared. Because we have the square root of x squared plus 1 over the square root of x squared. They're both square roots, so you can put them in the same square root. Okay, so that's what we're going to do. Now I'm going to go ahead and put the limit thing back on there. We're going to take the limit as x goes to negative infinity. Well, this has the same exponent. So those are going to, you can cancel those out and just take the leading coefficients, so you'll end up with negative 3. The second term is 0. 1 divided by negative infinity is 0. 1 divided by positive infinity is 0. Any number divided by infinity except infinity itself, or 0, is not even 0 divided by infinity is 0. Okay, so that's what you get from the top. In the second part, you get x squared over x squared, which is 1. And, you know, we could just cancel out and say it's 1. We don't have to do anything special. And then this goes to 0 because 1 over infinity squared is 0. So it's plus 0. So we get negative 3 over negative the square root of 1. Square root of 1 is 1, so you get negative 3 divided by negative 1, which is positive 3. So let's just plot this thing, see what it looks like. So the function is negative 3x plus 1 divided by the square root of x squared plus 1. And so you can see that I get positive 3. It comes up here. When x goes to positive infinity, you get negative 3. When x goes to negative infinity, it approaches positive 3. So we can go back and see that that is the case, what we found out here. So, push the wrong button there. So you can see we got positive 3. Okay, we'll go to 32, which is the trig one. So we have the limit as x approaches infinity of x minus the cosine of x divided by x. And what we can do is we can break that up into two fractions, x divided by x, which is 1, minus the cosine of x divided by x. Well, the limit as x approaches infinity of 1 is 1. And even though this term does not approach 0, it's going to become small relative to x. So we get, we might go from minus 1 over infinity, or minus 1 over 100 million, and then to plus 1 over 100 million and 1, or whatever. But it's always, this ratio is going to approach 0. It's never going to equal 0. So the answer is it's going to be equal to 1. Let's go ahead and plot that as well. Push the wrong button again. So the function was x minus the cosine of x divided by x. So we graph it, and you see this is what it looks like. And if we zoom out in the x direction, you see it's wiggling back and forth, but the wiggles get smaller, 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 and we approach y equals 1, which was the answer to the problem. Okay, this is problem 57. So here's the function. Y is equal to x divided by x squared minus 4. So we're asked us to find the extrema, intercept, symmetry, and asymptotes, and use a graphic utility to verify results. So the extrema you find by taking the derivative of the function. And in this case, we do have to use the quotient rule because it's not something we can rewrite. So let's say f of x equals x, g of x equals x squared minus 4. So f prime of x equals 1, and g prime of x equals 2x. So the quotient rule says we take this 1, so we take 1 times x squared minus 4 minus x times 2x, all divided by x squared minus 4 quantity squared. So we get x squared minus 4 minus 2x squared over x squared minus 4 squared. So that becomes negative 4 minus x squared over x squared minus 4 quantity squared. Just make sure I did that right. Okay. So when is y prime equal to 0? That's where you find the critical numbers. So we say 0 is equal to negative x minus x squared, basically x squared plus 4 equals 0. It turns out there are no solutions to that. So we don't have any, there are no extrema, if I did that correctly. Because there are no places where this becomes 0. Just still bothers me something. Yeah, I don't see anything wrong. I'm just going to check the answer book just to make sure. So this is 57. Section 3.5. 57. Okay. Yep, so there are no extrema. So we'll find that out when we plot it. So that is correct. The next thing we want to do is find the intercepts, 2 intercepts. So all we have to do is you look at the original function, you look at the numerator, and you say, okay, when is the numerator equal to 0? Well, when x equals 0. So we have an x-intercept at x equals 0. And then and our y-intercept, the y-intercept is when you set x equal to 0. So you get y is equal to 0 over 0 squared minus 4, which is 0. 0 divided by negative 4 is 0. So we have both the x and y-intercepts of 0. Okay, so that was the second part. Symmetry. Yeah, that's always hard for people to do, and I really don't think it adds a whole heck of a lot. So we're going to skip that part. And then you have the asymptotes. Well, let's go back to the symmetry thing just for a second. Maybe I'm blowing off that too easily. So symmetry is, what happens when you go negative x versus positive x. So I think what you would do is you would say, okay, if you put negative x in there, how does that compare with positive x? So if you put negative x divided by negative x squared minus 4, you get negative x over x squared minus 4. How does it compare with the original equation? If you just put x in there, you'll get x over x squared minus 4. So there's symmetry, but it's the negative version of it. So it's not an even kind of thing, it's kind of an odd kind of thing. We'll look at that when we get back to it. In asymptotes, so we take the so we let, what happens to this is, so the question is, what is the limit as x goes to infinity of this? And the answer is it's going to be 0, because you're going to have x to the first power over x squared, looking at the highest order terms. And the same thing applies for negative infinity also. So to the limit as x approaches negative infinity, you get the same thing. It still goes to 0. So I'm going to add a page, and then we're going to go make it, and then we'll take a picture. So what's the function? Y equals x divided by x squared minus 4. Okay, I need to zoom in. Okay, so there we go. And we'll take a picture of that. Actually, you didn't see that, but it doesn't matter because here it is. And let me zoom in a little bit. Okay, so there you go. So it said there was an x. There were no extrema, which there are not. There's no mixed local minimums and maximums. The x, y-intercepts are 0. You see you have vertical asymptotes at plus or minus 3. And what else did we say? Horizontal asymptote was 0. You see they both go to 0, but one from the positive side, one from the negative side. And as far as symmetry is concerned, notice that how this mirrors that, except it's flipped up. If it was an even function, it would go something like this, and then it would be, and this would go up like that, so it would match those. So f of negative x equals x of positive x, where here f of positive x equals negative f of negative x. That's the way it works. Okay, we're on problem number 59 now. So this is kind of in preparation for the next section, so that we'll go into even more detail. So this is our function. We're asked to find the extrema. So again, we're going to take the derivative. So let's call f of x squared. G of x is x squared plus 9. F prime of x is 2x. G prime of x is equal to 2x. So the derivative using the quotient rule is we multiply these two together. 2x times x squared plus 9 minus x squared times 2x, all divided by x squared plus 9 quantity squared. So we square that, and you can see what will happen is this 2x squared times 2x times x squared is 2x cubed, and then you have minus 2x cubed. So the only thing that's left at the top is 18x, and that's all divided by x squared plus 9 squared. So that's the derivative. When is this equal to 0? When the numerator is equal to 0. The numerator is equal to 0 when x equals 0. Therefore, we have a critical number at x equals 0. Now, is this a kind of a minimum or a maximum? Well, you can use the first derivative test or the second derivative test. I think I'm going to use the second derivative test, which does require me to take the second derivative, but it shouldn't be too bad. So we have y prime. Well, let's use the quotient rule again. So we have f of x is 18x. G of x is equal to x squared plus 9 squared. So the derivative here is just 18, and g prime of x is 2x squared plus 9 to the first power times the derivative of u of x, which is 2x. So we get 4x times x squared plus 9. And so we do this in the quotient rule for the second derivative. Y double prime is equal to 18 times x squared plus 9 squared minus 18x times 4x times x squared plus 9, all divided by x squared plus 9 to the fourth power. Now it turns out that we can cancel out one of these x squared plus 9s because we have one here and one there. So the denominator becomes x squared plus 9 cubed. And this term becomes 18 times x squared plus 9. And this is minus right there. Minus 18x times 4x. Because this one cancels out, and one of those cancels out. So we're going to do multiply all this stuff out. So we'll get 18x squared plus 72 minus that's 72x squared, all divided by x squared plus 9 cubed. Well, the denominator is always going to be positive because you square a number and it's going to be positive. So you have a positive number here cubed, which would be positive. So all we have to do is look at the sign. What we're looking for is y double prime at x equals 0, positive or negative, question mark. And so that's pretty easy because we just stick in 0 and we get y double prime is equal to 72 divided by some positive number. So it's positive. And because it's positive, then it's concave up, which is a minimum. So we have a minimum at x equals 0. Okay, now what are we doing next? Intercepts. Well, the intercepts, we just go back to the original equation and set the numerator equal to 0 and find out what values of x cause that to happen. So we get x squared is equal to 0, so x is equal to 0. So that is also, that's the x-intercept, and it's also the y-intercept. Symmetry. Let's try our thing we tried earlier. If we put a negative x in there for x, you'll see when we square negative x, we get positive x. And when we square negative x, we'll get positive x squared. So you can see it's the same equation. Positive x is this, negative x is that. So it's gonna be more symmetry like this, probably something like this type of function. And actually, it's not going to do that because it's not going to have a vertical asymptote, but we'll see when we plot it. And finally, the asymptotes. So what is the limit as x approaches infinity of the original function? The answer is 1 because we have the same exponent, so we just take the ratio of leading coefficients. And it's also true for negative infinity. Same thing, still get 1. So we're going to have asymptotes of 1. So that's what we can find out from all this stuff. So we're going to just hold on a second while I plot this function. And we have x squared divided by the quantity x squared plus 9. And let's take a picture of it. So there you go. What did we find out? We have an x and y intercept there. We have a local minimum. Is that what we said? Let me zoom out a little bit here. So we said it was concave up, so we had a minimum. So you can see it's concave up at that point. This is interesting. We do have a horizontal asymptote of 0, but we do have a case where there's a concavity. Well, we didn't actually have to answer that question. If we went back to here and if we solved this equation, so what was it? Negative 64x squared plus 72. Set that equal to 0, you find that there are 2 points of inflection which happen about right, probably about here and here. This is concave concave up, and then this is concave down. But they didn't ask us to do that in this problem. This is problem number 61. So our function is y is equal to 2x squared over x squared minus 4. And remember, what we're doing is finding the extrema, the intercepts, symmetry, and asymptotes. So to find the extrema, we're going to find the critical numbers, and we'll also use the second derivative test here to find whether they're minimums or maximums. So the equation, we're going to use the quotient rule. So the quotient rule says we have the numerator and we have the denominator, and then we take the derivative of each one of those separately. So derivative of 2x squared is 4x, derivative of x squared is 2x. So the quotient rule says the first derivative is going to be equal to this product, f of prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. So let's multiply this thing out. We'll get 4x cubed minus 16x, and then we get minus 4x cubed. And so these cancel out, and you just get negative 16x divided by x squared minus 4 squared. So that's the first derivative. So the critical numbers are going to be when the numerator is 0, or when the denominator is undefined. So there's really three solutions. One is the numerator is equal to 0 when x is equal to 0, because 16 minus x equals 0, and then you solve for x. And you also have critical numbers at x equals 2 and x equals negative 2 if you factor x squared minus 4. Now, this is when f prime, or y prime, I guess in this case, y prime equals 0. This is when y prime is undefined, does not exist. Now, we also know those are location of vertical asymptotes, so we really don't have to worry about those, even though those are critical numbers. We're not going to do it. We're not going to do anything about it. Okay, so that's the first derivative. Then the second derivative, we take the derivative of this equation. So again, we're going to call the numerator negative 16x and the denominator x squared minus 4 squared. So the derivative of that is just 16, and the derivative of the second part is going to be 2 times x squared minus 4 to the first power times 2x. Okay, we take the exponent, multiply by the argument, raised to the 2 minus 1 power, and then take the derivative of what's inside, which is 2x. So that gives us 4x times x squared minus 4, and let's just go ahead and multiply it out while we're at it. So that's 4x cubed minus 16x. Okay, that's correct. So now we plug that into the quotient rule again. So we can say that y double prime is going to be negative 16 f prime of x times x squared minus 4 squared minus the product of the other two, which is negative 16x times 2. Well, actually, let's not go this far, because we can use that to simplify it. So So what we have is negative 16x times 4x times x squared minus 4, all divided by x squared minus 4. We square that, squared, so it becomes the fourth power. Now, the reason I didn't cancel that is because you can always, there's always going to be this factor x squared minus 4 in both terms. So we can get rid of one of those. So you have negative 16 times x squared minus 4. That becomes to the first power. And then we get plus, so this is going to cancel out. One of these cancels out. So all we have left in the second part is 16 times 4, which is 64. You get a negative times a negative, so that's plus 64x squared. That drops out, and the denominator is now x squared minus 4 cubed, because I took one of those and canceled it out. And so we multiply that out. You'll get negative 16x squared plus 64x squared, which is 48x squared plus 64. Negative 16 times negative 4 is positive 64, all divided by x squared minus 4 cubed. And you see we had a critical number here at x equals 0. If you plug x equals 0 in there, you get y double prime is going to be, well, 64 divided by negative 4 cubed. Well, negative 4 cubed is negative 64. And so that becomes negative 1. So the second derivative at x equals 0 is negative. So we have a, well, it's concave down, because its second derivative is negative, concave down. We have a maximum at x equals 0. Okay, so that's the extrema. One extreme at x equals 0. It's a maximum because it's concave down. Okay, now back to answering the intercepts. We have to go back to the original equation. So let me just write that down. Y is equal to 2x squared over x squared minus 4. So the x-intercept is where y equals 0, and y equals 0 when the numerator is equal to 0. And that's the case when x equals 0. So our x-intercept is x equals 0. The y-intercept is when x is equal to 0. So if we plug x equal to 0 in there, we get y is equal to 0. So the origin is both the x and y-intercept. Then symmetry. Okay, so let's do our thing. If we put in negative x, we just end up, negative squared becomes 2x squared over x squared minus 4, which is the original one. So this is an even function. So that means basically f of x is equal to f of negative x. You can also see it's an even function because it's squared, but this is the reason. So that's symmetry, the asymptotes. So the asymptotes are when the denominator goes to 0. So the denominator, so that's when x squared minus 4 is equal to 0. So you factor it. And so you can see we have asymptotes at x equals 2 and x equals negative 2. Those are vertical asymptotes. So vertical. You get the vertical ones by setting the denominator equal to 0. Then you have your horizontal, and that's basically the limit as x goes to infinity of x squared, 2x squared over x squared minus 4. So we look at the highest order term, which is the x squared term, and they're both the same. So the answer is just going to be the ratio of the leading coefficients. So the answer is going to be 2. So the limit, and this also applies for negative infinity. The only time they don't work out that way is if, well, if this was 3, then you could have one going to negative infinity, one go to positive infinity. Or if you have that square root thing that we've done before. So that's the horizontal asymptote, the vertical asymptote. So I'm going to add a page, and I'm going to go to the graphing program, which the screen will go blank here while I plot this. So the function was 2x squared divided by x squared minus 4. I graph that. And I need to get my camera so I can take a picture of it. So there's the function. So let's see if it does everything we said it's supposed to do. Okay, the first thing we did was said there was one critical number at x equals 0. Okay, critical number, remember, is where the slope is 0. We actually have 3 critical numbers. The other 2 are negative, positive 2 and negative 2. 0 is the one where there's the 0 slope. So we either have a minimum or maximum. Well, that's not true either. If the second derivative is non-zero, then we have either a minimum or maximum. In this case, we said that if we go back and look at the second derivative at x equals 0, so we'll go back to the second derivative here. We said the second derivative is negative, therefore it was concave down. So let's go back and see if that's true. Yes, it's concave down. Why is it concave down? Because the inside of the curve is pointing downward. So this is concave down. This one turns out to be concave up. And this one is concave up. So if we were to have made up a table, we would have had 3 intervals from negative infinity to negative 2, negative 2 to positive 2, and from positive 2 to positive infinity. Okay, so that was so because this was concave down, it was a peak, which is a maximum. So that was the extrema. We said there was one intercept, which is at 0. You can see that's true. You can see its symmetry, how it's f of x is equal to f of negative x in all the cases. And the asymptotes, we said we had vertical asymptotes at x equals negative 2, and a vertical asymptote at x equals positive 2. So that's true. So they're going to positive infinity and negative infinity. And the horizontal asymptote was x equals, or y equals 2. So you can see if I draw a line from here outward, a line from here outward, you can see that the function is approaching 2 in both going to positive infinity and going to negative infinity. This is problem 67. So this is the third, I guess, in the sequence of, oh, actually it says sketch. I never noticed that. So I should have done that in the previous ones, but you saw the graph, so that's good enough. Okay, anyway. The function is 2 minus 3 over x squared. So we can either solve it as this or we could find a common denominator. Probably easier just to solve it as such. So the first derivative is going to be equal to, well, before we do that, we have to rewrite the second term as that. So when you take the derivative of 2, you get 0, and then here you get negative 2 times negative 3 is positive 6, and x to the minus 3 power. So we can rewrite that as 6 over x cubed. That's the first derivative. Let's go ahead and take the second derivative. So we can actually take the derivative from that version. So you get negative 18 x to the minus 4 power, or negative 18 over x to the 4th. So those are the first and second derivatives. So the question is, to find the extrema, we find any critical numbers first. Critical numbers. Question mark, when is that? That's when y prime is equal to 0. So that means we just look at the numerator. 6 is never equal to 0, so there's no critical numbers from the case where y prime equals 0. We do have 2 critical numbers, other ones, which are, well, one more, which is at x equals 0, there's also a critical number. And that's because it's not defined. But when you have, if the function is not originally defined at that point, then you can't have a derivative or a second derivative. So there's no way that you could have a minimum or maximum because it doesn't exist. So there are no extrema in this particular case. As far as the intercepts are concerned, use the same thing. We take the original equation, and to find the x-intercepts, we set y equal to 0. So if we subtract 2 from both sides, we get that. And if we solve for x squared, we'll get 3/2. How did I do that? Well, I set this up as a ratio, and then you just move the numerators, this numerator to the denominator on the opposite side. So if I move this up to there, I get x squared. If I move that down there, to get 3/2, and the negatives cancel out. So then you can take the square root, and so what we get is we'll get plus or minus the square root of 3 over the square root of 2. And then if we multiply by the square root of 2 divided by the square root of 2 to get the radical number out of the denominator becomes 2, and the top becomes the square root of 6. So we get plus or minus the square root of 6. So we have 2 x-intercepts. The y-intercept is when x equals 0. So you'll see that when x equals 0, the function is not defined. So when x equals 0, f of x does not exist. So there is no y-intercept. Okay. Symmetry. So let's write the thing down again. Y is equal to 2 minus 3 over x squared. So if we put in negative x, then it's squared, so it's going to be, you're going to be back to the original function. So it looks like it does have symmetry, and it's an even function. Okay, and the final thing are the asymptotes. So the asymptotes, we have 2 vertical asymptotes, the 1 vertical asymptote. Again, the original function is 2 minus 3 over x squared. So this part, so we have vertical asymptotes. At x equals 0. That's why it doesn't exist, because if you put 0 in here, it goes to infinity. And the horizontal asymptote Again, what that is the limit as x goes to infinity of the quantity 2 minus 3 over x squared. And that is the same as the limit as x goes to infinity of 2 minus the limit as x goes to infinity of 3 over x squared. Okay, well, the limit of the first part is just 2, and the second part is 0. You get 3 over a very big number, it goes to 0, so the answer is 2. And you can see if I put negative infinity, it would be the same answer. So the horizontal asymptotes are y is equal to 2. Okay, now given that information, we'll actually graph it this time, since I remembered. So let's put in a piece of graph paper. So there's the graph. Okay, so there were no extrema. There were vertical asymptotes at 0, so let's put that in there. So I'm just going to use a blue line for my vertical asymptote. We had 2 x-intercepts, which were square root of 6 over 2. So what is that? Get your calculator out. Square root of 6 divided by 2 is 1.2. So we'll put one little dot there and a negative 1.2. So those are my x and y intercepts. And we have a horizontal asymptote at y equals 2. So I'm going to draw that out here. And we have vertical asymptote. And notice, if it goes here, it has to go through, then it has to go to negative infinity. It wouldn't, I guess theoretically you could come down here and then you go back up. But this is the horizontal asymptote, and then it goes through this x-intercept and then goes down to negative infinity. And then the same way with this thing. It starts out here below the curve because it can't come above. And like that. Okay, so we're going to add a page, and then we'll plot this, and then we'll see how they compare. Oh, sorry, getting carried away here. So we have 2 minus 3 divided by x squared. And there it is. There's my camera. Take a picture. So we're back, and there you go. So let's just draw the things that we talked about. You've got a horizontal asymptote. We have a vertical asymptote. We have an x-intercept. Let me put this on one page so we can see it a little better. And the x-intercept is right there, which is 1.224. And we have one there that's positive 1.224. And if we looked at the second derivative, we'd see these are both concave down, which I don't think well, let's just go back and show that's true. Show that the second derivative is always negative, which means concave down. So here's the second derivative. So you can see the denominator is always positive because it's the fourth power. So you're going to have a negative number times divided by a positive number. So this is always going to be negative. Therefore, the function is always concave down, which is what's true in this particular case. Okay, so we're going to look at problem 87. And what that's talking about is the difference between Einstein's theory and Newton's theory. Newton's theory, for you guys in physics, we know that velocity, if you have a constant acceleration, velocity is equal to the initial velocity plus the acceleration times time, which is just a straight line. So if we draw a straight line, the slope being a, in this case, on the graph, they're starting at rest, so the initial velocity is 0, v0 is 0, and you end up with this thing. So this is velocity, this is time. So according to Newton, if you have a certain acceleration, if you applied a force and got an acceleration, ultimately it would just continue to get higher and higher in velocity forever. Now there's a velocity, special velocity, which is the speed of light. So this is going to be c, and c is equal to 3.0 times 10 to the 8th meters per second. And what Newton's law says is that when you get closer and closer to the speed of light, then it's harder and harder to get there, and ultimately it will never reach the speed of light. So what we're looking at here is this is the Einstein prediction, and so we're looking at a horizontal asymptote. The horizontal asymptote is the speed of light. So it says functions n and e represent the predicted velocity. Write a limit statement that describes each theory. So the Newton theory says that the limit of v as t approaches infinity, it's going up to infinity, equals infinity. It just keeps going forever. So it does not exist. You can go at any speed. Whereas Einstein the right way to spell it? No, actually the way around. I was trying to go I before E except after C, but apparently that's not true for Einstein. So for Einstein, the limit of the speed as t approaches infinity is equal to c, where c is the speed of light. And that's it. Okay, the last problem is 88. It's a similar kind of thing. This is actually what's called Newton's law of cooling. We saw this in the one of the previous sections when we were talking about the, I guess when we were doing the mean value theorem. But if you start with something at its temperature and you expose it to air, it's gonna follow a curve like this, which turns out to be exponential in nature. So this would be your initial temperature, and this would be your ambient temperature. We call that T infinity. That's just the temperature, or we could call it T0, I guess. T0, that's the temperature of the surroundings. And so what's going to happen is this thing's going to approach this value, and ultimately it's going to be so small that there's no difference. And in our particular case, at T equals 0, the temperature is 425. And 72 is the ambient conditions. So it says find the limit as t approaches 0 from the plus side. What does this limit represent? So the limit of t, so this is the temperature and this is time. The limit of t as t approaches 0 from the plus side equals 425. What does that represent? That represents the initial pi temperature. And so for part B, it's asking what is the limit as t approaches infinity, of time approaches infinity. That's equal to 72. And they put degrees Fahrenheit, so we can put that there. Degrees Fahrenheit. So the answer is 72, and that's the, what do they call it? Well, we'll just call it ambient temperature. That's the temperature of the air. And because the air is, there's so much air, it never, if you had this pi in a box, then this actually would increase. But if this is the temperature of the air, which we assume is an infinite supply of relative to the pi, then it's going to be 72 degrees Fahrenheit.